Hey everybody, welcome back to Young Engineers of Today. We're going to continue with model rockets um, and do more with that. So we're probably going to spend some time reviewing what we went over on Monday, just a little bit of time, not too crazy. I know I went through everything pretty extensively, so it's not like you guys necessarily need it, but it's always good to get a refresher. And then we'll move on to the next presentation, which is going to be a lot more in-depth about the design specifics. Now we're probably really only going to get through fin design today, if that. But we'll make it as far as we can. How's everybody doing, by the way? Good. Yes. Yes. Good. Also, I want to just because I feel like I should. Oh, good. I'm glad to hear it. I feel like I should disclaim, if I seem a little scatterbrained today, I'm running on 2 hours of sleep. So take everything I say with a grain of salt. There is probably going to be some trailing off and some meandering that's going to happen just because most people don't operate very well on 2 hours of sleep. I won't get into what exactly happened there, but anyway, just so you guys know. But we'll hopefully it just means it's going to be a more entertaining presentation than normal. So anyway, on Monday we went over just model rockets in general, why and the parts and the similarity to real rockets, sort of. We'll go a little bit more over the similarity to real rockets. There's not a whole lot more there though. But yeah, model rockets are smaller versions of rockets used in spaceflight, hence model. Duh. Many of them emulate early rocket designs, however they can be whatever you want if you're patient enough, like this little model of a Saturn V here, because you can customize them to make them look like really whatever you want. Within reason, obviously. You can't make like a bowling ball or something like that because it's not really going to fly all that well, even with model rocket engines. I'm sure if you slapped on enough, but I don't think you want to slap a bunch of model rocket engines on a bowling ball and let that thing fly, because then you've got a very fast moving bowling ball, and that would just be bad for everybody involved. But for the most part, they can be there is a certain degree of customization that model rockets offer. And why specifically? Well, because they're fun. They're enjoyable to build and launch, but they can be useful to teach the basics of aerodynamics and rocket design and construction. So there's that as well. The reason they can be used to teach all these things is because model rockets share a lot of similarities with real rockets, but, a model rocket basically has a nose cone, a body, and fins. No surprise there. Fins provide stability. The body contains all of like the recovery systems and everything like that. The nose cone increases the aerodynamics of the rocket, decreases the drag. The inside, though, you're going to have your engine and your parachute or some sort of recovery system, your shock cord, things like that, the engine mounts. Basically, the engine makes it go up. The engine mount makes sure that the engine doesn't go anywhere. The recovery wadding makes sure that when the engine deploys its ejection charge, that is to say, its blast in the direction that goes inside the rocket, the recovery wadding absorbs a lot of that heat and force enough so that the parachute and stuff like that isn't damaged, but it still deploys. Parachute or the recovery system in general makes sure that the rocket floats down more or less gently as opposed to just crashes down to the ground and gets damaged. Shock cord keeps the nose cone connected to the rocket, ensures that that the nose cone being blown off doesn't actually stress the rocket body or the rocket in any way. Parachute lines keep the parachute attached. Duh. Launch lugs keep the rocket attached to the launch rail so that it when it's lifting off, it has enough time to gather speed to allow the fins to be effective. And then we talked about what was actually inside of the engine itself. The model rocket engine itself tends to have a few stages to it. There is, of course, the clay nozzle, which provides a bit of directed thrust so that the rocket will actually have more thrust downwards so that it will go up more effectively and faster. The propellant is what actually is basically the rocket fuel. That goes off in order to make the rocket go up. The delay charge and tracking smoke is basically just some dead time in the rocket's launch so that it can continue to coast upwards and not immediately deploy the parachute and harm the rocket because it's going too fast. In addition, it also provides, or slow it down as well, it also provides some smoke so that you can more easily see the rocket up in the sky because it tends to go up sometimes kind of high and kind of hard to track at that point. And then you got the clay cap and the ejection charge. The clay cap mostly just protects the rest of the rocket against most of the heat of the ejection charge and also provides something that gets shot upwards to force the rocket to deploy the parachute and all that kind of stuff. So with all that put together, a typical launch will be, you've got your rocket sitting on the launch pad, it ignites, you've got your power descent, which is where the propellant is burning. The propellant runs out, then you have coasting where it's the delay charge is burning. Usually you get a little bit of smoke out here as well. Then the delay charge runs out and you get the ejection charge. The ejection charge fires, the nose cone pops off, the parachute comes rolling out, or the recovery material or whatever deploys and allows the rocket to descend slowly back down towards the ground. And you can pick it up and do it all over again. Replace the engine, put in some more recovery wadding, repack the parachute or recovery, whatever, and then do it all over again. So that's essentially the very, very basics of model rocketry. Now, it doesn't cover everything, obviously, but it does sort of give an idea of how these things all sort of work together in order to create this flight path. The launch lugs keep it attached to the launch rails so that it launches more or less straight. The fins engage during power descent because it's going fast enough to keep it going in the same direction. When the propellant runs out, then it goes into coasting flight where the fins are still working, although not nearly as well as it slows down. The rocket becomes more top-heavy as it expends its propellant, then starts to turn. The ejection charge blows. The clay cap comes shooting off. The recovery wadding protects the blow, but forces the nose cone to pop off and the parachute to come out, and then it descends down. So all the parts of the rocket basically get used. A rocket is a very tightly designed thing in which everything has a purpose. Now, how does this compare to full-size meant-to-go-to-space rockets? And we covered this on Monday, but go into it in a little bit more depth. So again, an actual rocket is going to be set up a little bit differently from model rocket, but there are similarities there. And of course, actual rockets will differ from design to design as well. So you're not always going to see an actual rocket look like this on the inside and look like this on the outside and everything like that. This is a very simple rocket. Again, this is what a lot of model rockets are based off of, but this is a very simple rocket. So you've got a sort of recovery system. Now the payload system up here in the nose cone, this can be whatever, but this can also include a recovery system, even if it's just for the nose cone itself and the payload that's inside. Model rockets are a bit unique in the sense that more of them tend to be recoverable than much of real-life rockets. A lot of that has to do with the fact that real-life rockets or spacefaring rockets or whatever go a lot higher, in this case space, or the edge of space, and they have a lot further to fall. On top of that, a lot of times they're just kind of meant to burn up in the atmosphere on reentry. A lot of these rockets are meant to be disposable and just kind of be disposed of that way. That is, of course, if they're ever meant to return to the surface at all. There are a fair number of rockets as well that fly up into space, get into orbit, expend their payload, and then they float in space as space junk. Not ideal, but it is something that we as humans have done for a very long time now. Now it's something that we're trying to get away from as well, because space junk is becoming a very real problem, but it is something that exists. You know, if you've ever seen the movie Gravity, that is something that sort of explores the repercussions of space junk. So there's that as well. But regardless, that meant to go to space, life-size rockets, whatever you want to call them, don't tend to return nearly as well as model rockets do, because model rockets don't go as high, they're lighter, they are smaller, which tends to make them more structurally sound. Like the strength of the material is basically more effective at smaller sizes. This is sort of a physical phenomenon where you can have something that's very small and it's going to be very tough compared to something that's very large but made out of the same material with the same shape, same dimensions, like same ratio of dimensions and everything. And that's just because as things get larger, the weight of the actual material itself becomes a burden as well. And you see it in living and non-living things. Like people always, say like, oh, if an ant were the size of a building, it could lift up a city. And it's kind of like, okay, assuming everything, scaled up properly, but in a lot of situations like those, an ant wouldn't actually be able to stand under its own weight if it was the size of a building. A lot of the reason why an ant is so strong is because it's so small. This seems like sort of a tangent, but model rockets can be sort of a similar thing because they're small and they're light and they're made out of a little bit of material and stuff like that. They can actually withstand impact better than big rockets can. So it can be a lot harder to recover that kind of stuff. And that's why you see this recovery system looks vastly different. And that's why a lot of times the recovery system tends to be just for the payload of a rocket. You've got the engine here, or the propulsion system, whatever you want to think of it as. In a model rocket, it's much smaller, relatively speaking, because again, it doesn't have to go as high. A model rocket is much lighter. And for that reason, you don't have to worry as much about fuel weight versus thrust and stuff like that. There is a lot more fuel present in meant to go to space rockets for multiple reasons. One, because space is a lot higher up, and also because you start to reach a point where you need more fuel in order to lift the fuel that you need to lift the rocket into space. And there's certainly a point of diminishing returns where you start having so much fuel that, the rocket is no longer able to get itself off the ground until it burns off some of its fuel. But regardless, this is a quandary that engineers have to deal with, aerospace engineers have to deal with. And honestly, the best solution is to find more effective and efficient fuels with higher, specific impulse and things like that. But that's another discussion for another day. Point being, this has a lot of fuel. The rocket on the right has a lot of fuel because it needs to go a lot higher, and also because it actually has to expend some fuel in order to lift up the fuel that it already has. And it's weird and kind of counterproductive, but this is sort of the life we live as, humans trying to get things into space. These are the constraints we deal with when we live in a gravity well like Earth's. And then you see that I've put a green box around the fins on each of these rockets as well. Green probably wasn't the best idea. Let's go ahead and make this, I don't know, purple, pink. Let's make them pink because the pink will stand out more against the green fin on the right rocket. But these are your control, well, I'm going to call them control surfaces, not necessarily a correct term when you apply them to model rockets. Control surfaces refer to like ailerons and rudders and things like that, and certainly the rocket on the right will have stuff like that because those fins will be controllable. You'll be able to flip flaps on them. As silly as that sounds, you'll be able to flip flaps on them, on those fins and stuff like that, in order to provide control to the rocket. to keep it going upwards and stuff like that. It's not going to be like the rocket on the left, the model rocket, where the fins are meant to just sort of keep the rocket in the same place, and we are banking on the fact that the rocket will go in a generally upwards direction. You know, as you get further and further up into the atmosphere, and as you accelerate more with a rocket, you'll start to introduce precession, which is basically just sort of gentle wobbling of the rocket, tilting, things like that, where, you know, a design like the model rocket on the right will be able to fight against that where the atmosphere is thickest and where it's going the fastest. You might need a little bit of help with something like the rocket on, or excuse me, the rocket on the left will be able to handle that, but the rocket on the right will have some issues because A, it's heavier, and B, it'll start getting into areas where there's sort of like less atmosphere to grab onto. So for that reason, you have helpers like flaps and ailerons and things like that to provide more directed airflow. Anyway, point being, the fact that there are flaps and stuff like that are technically what makes something like a fin or a wing a control surface, but I guess you can sort of kind of argue that a fin on a model rocket is also a control surface because it provides control for the rocket. It's just, generally it's referred to as a control surface because it is controllable. Anyway. This is just an interesting side note before we move on to the second presentation, but you may notice that many rockets don't actually have fins. You know, we build these model rockets and they have fins on them, and you might think of rockets with fins, but then you can also look at plenty of pictures of rockets and they don't have fins, which is sort of odd, right? Like I've been harping on the fact that fins provide stability and fins provide, you know, a means for a rocket to keep from veering off course and stuff like that. Why are there rockets that don't have fins then? What possible purpose could those serve? Why would you have that? You know, why would you deny yourself that additional control? Well, you don't always need fins in order to have control over a rocket. A rocket can also have gimbaled thrust. Now, you know, this is beyond model rocketry because gimbal thrust usually involves a guidance computer and some advanced servos and you know, a gyroscope and things like that. But essentially, you know, if the rocket starts to precess, as you can see here, tilting off course, the gyroscope will sense it. It'll send information to the guidance computer. The guidance computer will go, hey, we're off course, and it will actually tilt the nozzle at the bottom of the rocket in order to adjust the thrust so it's continually heading upwards. The rocket will actually correct itself by shooting the thrust slightly laterally. So that, I think, is kind of cool. The fact that we have rockets that can actually correct themselves by changing the direction that the thrust is coming out. But all in all, basically the point I want you to take away from this is the main difference between space rockets and model rockets is their cost and their power and their purpose. Model rockets are meant to go up a little ways, come back down, and just be like, oh, hey, aerodynamics, you know, fluid dynamics, things like that. Space rockets meant to go to space. They're meant to apply that knowledge that model rockets will give you in order to take a rocket all the way into space. But they work the same way. They provide directed downward thrust using a chemical reaction. You know, they have the same concerns, recovery and stability and, you know, efficient use of fuel and things like that. They're very, very similar in those respects, and that's why model rocketry is a stepping point for a lot of people to move into aerospace. You know, there are a lot of people out there who say that, like, hey, you know, the reason why I got into the aerospace business, the aerospace engineering industry, is because I really loved model rockets when I was younger, and it really put me on this path, and I had a passion for it, and I really like to do it and all that kind of stuff. So that's a big part of the reason why. It's something that, you know, we still do. Yeah. Oh yeah, exactly. Liquid oxygen is shortened to LOX or LOX. Um, liquid oxygen, liquid oxidizer, and oxygen can be used to provide the chemical reaction in a rocket. And it works, because a lot of times, a lot of the chemical reactions that we use for rockets to fly and stuff like that um, require combustion. And combustion tends to require oxygen. So for that reason, you include oxygen in a rocket in order to provide the necessary oxygen in order for combustion to happen, so a rocket will still be able to fire in space. You won't be able to, for instance, fire a gun in space, like in a hard vacuum. You won't be able to fire a gun because it requires that gunpowder to ignite, and the gunpowder in traditional bullet casings and stuff like that doesn't, provide its own oxygen to ignite. So a gun won't go off in space. So for that reason, oxygen is included in a lot of rockets, a lot of liquid fuel rockets, in order to, you know, provide the thrust necessary for a rocket to get to space. My cat is flipping out. You can probably hear him in the background. But yeah, so that's lesson 1. Lesson 2 is more about the specifics of rocket design. Well, at least in a general sense, the general specifics of rocket design. Good Lord. Can you tell I'm tired? Most of this is going to be about fins and motors and recovery systems. And what I mean by that is different fin designs, how a different motor might affect how your rocket might fly, how high it might fly and stuff like that, and different recovery systems, getting a rocket back down to the earth gently. But we'll start with fins. Fins are, as you might have guessed, the main stabilizer on a rocket. Stabilizers are what stabilize the rocket's trajectory as it launches, to no one's surprise. In other words, stabilizers make sure that the rocket just doesn't fly every which way upon launch, just for the most part, up. But how your fins are structured can affect how your rocket flies. And how effective it is at flying upwards and how stable it is and stuff like that. So, it's always good to take a look at that and spend some time talking about it. But before we really get into it, it's important to understand the forces at work on a fin. The biggest one being drag. Drag is a force, and it's just the force of the surrounding air on the fin working to slow down the rocket. Think of it kind of like friction, but from the air itself. If you've ever been in a car before and you stuck your hand out the window, and you can feel the air sort of pulling your hand back, then you might try, so you might have your hand out sideways, so your palm is facing towards the ground, and you can sort of do like that, my hand is flying kind of a thing. I don't know, maybe you're not weird like I am. But then you might, while the car is moving, flip your hand so your palm is facing towards where the car is moving towards. So forwards, your palm is facing forwards, and then you can really feel the force of the air on your hand. That is drag. Drag always exists as long as there's an atmosphere and, as long as there's some sort of acceleration of some sort or velocity, movement. So drag is an ever-present problem for people who design rockets and airplanes and stuff like that, and it's something that you have to constantly think about and sort of not only counteract but twist it around so it's working in your favor and stuff like that. But it's a very real design concern for rocket designers. So it's something that we have to take into account when we're designing fins for these rockets. So drag on a fin comes in 2 forms. You've got induced drag and profile drag. Oh, wow. This is definitely a thunderstorm. I don't know if you could hear that thunder in the background, but I have the windows open, and it is definitely storming. Anyway, drag on a fin comes in two forms. You've got induced drag and profile drag. And as you can see here, I got a little diagram here showing the drag is actually, it's created by the airflow, but it's pushing down on the rocket and directly working against the thrust of the rocket. So that's actually something that when you're launching a rocket to go to space, funnily enough, you don't want the most thrust at the bottom of the launch. You actually want to ramp up the fuel usage as the rocket gets higher in the sky. Why might that be? Do you? Yeah, more drag somehow. Why might there be more drag? More airflow. Yeah, basically. I mean, the answer is actually deceptively simple. Sorry, I have to close the window before I totally just like soak the kitchen. So I'll be right back. So mission partially accomplished. Everything about a foot out from the window is soaked. But I did manage to close the window before the hail started falling, so that's a plus. Anyway, yeah, the atmosphere is thicker closer to the ground. There's more air. Literally, there is more air. So you actually, when you have that's one of the advantages that a liquid engine has over a solid engine. That is to say, a liquid fuel engine has over a solid fuel engine. Solid fuel engine being something like a model rocket would have. A solid fuel engine, you have very little control over how much it burns. Basically, it burns as much as it can, as fast as it can, and then it only stops when it runs out of stuff to burn. I am in Chapel Hill, so the storm is around here. Probably, there could be some storming happening in Raleigh. I don't know how big the storm is. Certainly, if not now, then at some point in the future. But right now, if you're in Chapel Hill, you got quite the thunderstorm on your hands. Oh, well, yeah, that's true too. North Carolina is pretty much if it's storming somewhere in the state, chances are it's storming in the other part of the state. When I say some part, I mean if it's storming in Chapel Hill, it's probably storming in Charlotte and vice versa. But anyway, solid fuel rockets just burn and burn and burn and burn and burn at the same rate until they run out of fuel. Liquid rockets, you can actually throttle the amount of fuel that's used. You can throttle the amount of thrust. And so that's a very common tactic, is actually to run at, I don't know, 70 to 80% maximum thrust when you're close to the ground. And then when you get to be a few thousand feet up and the atmosphere is thinner, then you can really crank it up to 100%, because otherwise you're actually just wasting fuel because the drag is so high. So for that reason, um, you meter your fuel usage. So induced drag and profile drag. Induced drag is created when the rocket fins use the air to correct a rocket's path. So this doesn't happen all the time. Most model rockets do very well at flying straight up, so induced drag tends to be low. It really only happens when the rocket whenever the fins are actually, I guess if you want to think about it this way, the fins are actually gripping the air to try and correct the rocket's path. They're fighting against precession or wobbling or something like that in order to keep the rocket flying straight up. That's when induced drag happens. Since model rockets are light and they're, generally pretty, they're using a tried and true rocket design, they tend to do pretty well at flying straight up. Plus we get launch lugs and stuff like that to help keep it going in an upward direction, get it started off on the right foot. So, induced drag is less of a concern when a rocket is flying. A model rocket is flying, certainly. Although it is something you still want to take into account, and it's something you actually want to make sure is happening at the right times. You know, you want to take advantage of induced drag to keep a rocket pointed in the same direction. Because if you make it so that there's absolutely no induced drag, well, that's great. You've reduced the drag on the rocket, but you have no means of fixing its path in case it suddenly decides to go sideways, literally. Now, profile drag, on the other hand, comes from the shape of the fin itself, and it's always present under velocity in an atmosphere, no matter what. So again, to go back to our earlier example, but sort of think about it in a different way, you could think of a boxy car driving down the highway versus a very sleek and like angular car. You know, a boxy car is going to have a lot of profile drag because it's a box. And like a semi or something like that is going to have a lot of drag along the front of it, a lot of drag and a lot of turbulence and stuff like that. And then you've got a nice Maserati or a motorcycle or something like that going down the highway, and it's going to have very little drag because it's going to have a smaller profile, and it's going to be specifically designed to sort of shift the air up and around it and stuff like that. So for that reason, you're going to have to think about profile drag. But because of this, you want to spend some time considering different fin designs in order to reduce the ever-present problem of profile drag while still taking advantage of induced drag to keep control on the rocket. Whoops. But there's another concept. I know I just keep introducing concepts, but in order to better understand how we can tackle fin design itself, there's another concept that's good to understand called a Reynolds number. So a Reynolds number is simply a coefficient or a ratio. It's a number. It's actually just a number that helps to describe how turbulent a fluid like air is. What? I'm saying right now. Air isn't a fluid, it's a gas. And, you'd be half right. Technically, fluids and liquids aren't exactly the same thing. Fluid can be synonymous with liquid in a popular sense, but in a physics sense, they aren't exactly the same thing. Think about what you can use the word fluid to describe. Things that flow and aren't solid, right? You think of something that's fluid and it moves and it. Yeah, exactly. Exactly. You get the idea, Benkai. So yeah, it's something that's it goes with the flow. It doesn't stay in one place. It's not rigid. It's very malleable and things like that. In a physics sense, both liquids and gases are considered fluids. So a liquid is a fluid, but a fluid isn't necessarily a liquid, which is kind of weird, but so like if you go into engineering, like mechanical engineering or aerospace engineering or something like that, you'll be taking a fluid dynamics class, and that will cover aerodynamics because aerodynamics are part of fluid dynamics. So anyway, back to this picture, because it's relevant. A Reynolds number describes whether a fluid is very smooth in its movement, or laminate, or very bumpy and chaotic, or turbulent, and where it actually happens, where the boundary between laminate flow and turbulent flow exists. So we can use this number to help predict how our fins will perform. And the reason why this picture is relevant is because this is actually a picture of the movement of air from a candle. This bottom part right here is the candle. And there's a flame, which we can't see because it's taken on a spectrum. I'm not entirely sure what, but this is actually air that we're looking at right here. All of this right here. So this bottom part is laminate airflow. You see how it's very smooth. It's all going in one direction, and then right about here, it just starts going crazy. This is turbulent. You're flying an airplane, and the pilot's like, hey, we're going to hit some turbulence, and then the plane starts to kind of wobble a bit and stuff like that, that is rough and chaotic airflow. It's rough and chaotic fluid movement. Versus how flights normally go, which is very laminate. You got a lot of smooth airflow over the wings and stuff like that. The flight is very smooth. That would be laminate. So we'll take a small moment to look at how a Reynolds number is calculated. Is it necessary? No, it's not. But it's kind of neat how we can use mathematics to predict something like air movement. Like, that's kind of cool, I think. It's kind of neat. Nature is pretty neat. Sorry, ever seen nature walk? So this right here, this is the equation that gives you a Reynolds number. Now, a Reynolds number can be used to not only predict the turbulence of a fluid, but also where that turbulence begins, which is pretty neat. So if we look over here, you got the Reynolds number, which is the result over here. The Reynolds number is equal to the density of the fluid times the velocity of the fluid, how fast it's moving. So, how dense it is times how fast it's moving times the length of the object that the fluid is passing over or through, whether it be like a pipe or a wing or something like that. And then the dynamic viscosity, which has to do with how it changes viscosity is like how thick a fluid is. So think about water. Now think about molasses. Water is not terribly viscous. Molasses is very viscous. Molasses is a very viscous fluid. So dynamic viscosity has to do with the basically how sort of resistant it is to change and stuff like that. So anyway, plugging all this stuff in, you can actually determine the turbulence of a fluid, and you can also predict where that turbulence begins. So in this example right here, you could use mathematics, you could use the Reynolds number equation to figure out how far above the candle the fluid becomes turbulent, which is kind of neat. So we mentioned that it relates back to how fins perform, but how does that work exactly? Well, we can use a Reynolds number to see if the fins are long enough to be useful. You see in this diagram right here, you've got some lines here. These represent the turbulence of the air passing over the rocket. We use nose cones to basically increase the aerodynamics of a rocket to reduce the drag from the top of the rocket on flying into the air. If like this was just a flat top, there would be tons of drag right here, and there would be tons of turbulence right here. But by using a pointed nose cone or a rounded nose cone, you decrease the drag because the air gets directed around it. However, air getting directed in general creates turbulence. So you can see that here with these wiggly wobbly lines. This turbulent air is actually very hard for fins to hold onto, to grab onto, and to correct a rocket's path. Fins really perform a lot better in laminate air or smooth air. So smaller fins won't be able to extend past the turbulent part of the air created by the rocket body, which means that they'll be less effective. Larger, longer fins will be able to make use of the laminate air that's around the turbulent air to keep the rocket steady. But we can't just make super big fins, right? Because doing that, we come back to profile drag. Because the larger we make our fins, the more profile drag they have. And of course, if they're constantly engaging and correcting the rocket and stuff like that, we're still going to have tons of induced drag, which means that even though we are, taking advantage of the fact that we know where the air is going to be turbulent, and we're making fins that are large enough to engage the laminate part of the air in order to keep the rocket corrected, and we've got enough induced drag so that we can have a rocket continue to fly stably and things like that. Just by virtue of the fact that the fins are large enough, they're going to have a lot of profile drag. So what do we do? You want to have the fins small so they don't have a lot of profile drag, but you want the fins large so that they can get to an area with a pretty high Reynolds number and that is smooth airflow. But, you know, we actually have a choice over that too. The actual shape of a fin starts to come into play now, and it becomes far more important how we construct the fin itself. So we know a large fin is probably pretty ideal, but what about the shape? And actually, I'll have you guys guess that for a moment. So we'll take a moment to consider the shapes to the right and maybe perform an educated or just wild stab in the dark guesses about what the best fin shape might be. What do you guys think? 1, 2, 3, or 4? We got we got a vote for 2, a vote for 1, a vote for 4, vote for 1, vote for 4. So right now 4 and 2 are the leaders. All right, all right. 3 votes for 4. 4 is the current leader. Yeah. All right, so I don't know, maybe some of you might have thought that an elliptical shape would have been the best one, like so 3. Nobody said 3, so apparently you guys are smarter than that. But, you know, look at that airplane, look at that highly technical piece of equipment. But, you know, kind of based on that, you might think like, oh, we want an elliptical shape because, you know, that's a tried and true design. That's what we use in aerodynamics already. But this is not a complete answer because you also have to take into account the ratio of the wingspan versus the size of the aircraft. In the case of airplanes, this ratio is pretty dang high, meaning that the wings are very large relative to the rest of the vehicle. Not so with rockets. You want the span of the fins to be as small as possible. You know, I know I said that you want them to be large, but you also want to make sure that they're as small as you can get away with, large enough to be able to take advantage of laminate airflow, small enough so that they're not creating a whole ton of profile drag. Rockets have to be much more efficient with their usage of fuel and tend to fight against the air because they're trying to, you know, get out of the air rather than use it to their advantage like planes do. Planes take advantage of the air in order to keep them up in the air. You know, they're sort of a fundamentally different design with the wings. Rockets, they're trying to cut through the air as quickly as possible and efficiently as possible so that they can get to the point beyond the air. They don't use their fins like airplanes do with wings. So for that reason, these types of not literally speaking, because it's not like you're actually cutting the molecules or anything like that. When I say cut air, I just mean like redirect molecules around the wings and stuff like that. Yeah, I mean, in a poetic sense, I suppose so, but in an actual sense, there would be a whole lot of energy released if molecules were actually being, you know, broken by planes flying past them or rockets flying through them. Whole lot of energy. Whole lot of energy. Can you imagine if atoms were being changed by it? Just nuclear explosions going off in the air. Little tiny ones. Anyway, for this reason, elliptical fins tend to do pretty poorly in situations with low Reynolds numbers anyway. So that is to say turbulent air. We already knew that from airplanes. But also the area by the rocket body is not going to do very well. We already knew this because we mentioned it up here. But they tend to do particularly poorly with that. Which means that they'll need to be larger anyway. Then on top of that, the fin near the body of the rocket tends to also be thicker and longer. Like you can see here in the expert modeler's fin's edge view, the part of the fin that's closer to the rocket is thicker than it is by the edge of the fin. So these cross sections are you know, progressively getting smaller. Now, granted, these cross sections are also progressively getting smaller, even though the edge view here is the same. But regardless, whichever way you go with an elliptical fin, you'll need to extend the fin further outwards in order to take more advantage of the largest part of the fin, because if you use a larger part of the fin, it will have, basically, it will be more effective at leveraging the air in order to keep the rocket stabilized. Now, granted, the edge of this is also going to have lower drag, but it's generally not enough to sort of counteract the fact that it's not going to have a whole lot of control either. So, and on top of that, the fin near the body is thicker, which increases the drag and exacerbates its issue with low Reynolds numbers. You can make the fin thinner towards the end, like I said, but that tends to be very difficult to make, especially if if you're just like, whittling it or something like that, who knows. And it's hard to guarantee strength and consistency. So, funnily enough, rectangular and parallelogram style fins do very well at lower Reynolds numbers. Just better in general than elliptical fins do. And on top of that, their area stays more or less consistent across the entire length of the fin. So when it's in the laminate area, it has just as much effectiveness. Like there is just as much surface area to work with everywhere on the fin. So if you make your rocket body more aerodynamic so that there is less turbulent air near the base of the fin, then the base of the fin will be, that's just a bonus, because the closer you get to the base, you have the same exact effectiveness. Whereas here, it's kind of a necessary thing in order to engage the more, the larger parts of the fins and, have more surface area there. Now, this isn't to say that your rocket won't fly, well, necessarily with elliptical fins. It just will tend to fly better with rectangular fins. So, something to consider. And yeah, rectangular fins are going to have more drag because they're going to be generally thicker and larger anyway, but they perform well enough to offset that and then some. So overall, you have, generally better control. This is all a bit counterintuitive, but, math and physics are funny like that sometimes. But that's why engineering is an iterative process. Sometimes the crazy seeming ideas are the ones that work out the best. Once you've exhausted all the things that seem sane, you go like, hey, let's try rectangular fins. And somebody's like, well, that's dumb, but I guess we got nothing else to try. And they fly it and they go, hey, that actually worked out pretty well. I won't get started on motors yet because that's going to be our topic for next Monday. But yeah, I think we got through that at a pretty good clip. Covered a decent amount of information on fins. A lot more than you might have thought. You might be like, oh yeah, fins should be triangular shaped because they should be. But there's actually a fair amount of math that goes into it, and I've really only introduced you guys to the very surface of it. Like we just scratched the surface. Nothing crazy there. But yeah, so anyway, why don't we go ahead and do the poll questions, and then we'll leave it open to question and answer time. So we have as much time as possible to do that before we break for the weekend. After the poll questions are done, you know the drill. If you don't have any questions, you're more than welcome to head out. Have a wonderful weekend, and we'll see you on Monday. Otherwise, I'm here, and we can talk about stuff. Anyway, yeah.